All right, so continuing on with the rational root theorem, we have several more practice problems using the rational root theorem. Hopefully it'll sink in by the time we get done with those three. Remember, once you have determined the possible rational roots, that's these guys right here, use synthetic division. We modified our synthetic division to look like this so that it wouldn't take up so much space to find them. Remember, once you find one, you can use the resulting polynomial to find the next. So once we found 2 on this one, the resulting polynomial is sitting right here, 15x squared minus 2x minus 1. You can continue using the resulting polynomial to find more roots. You don't have to go all the way back up here. Once you get it down to a second degree polynomial, so here we are, use factoring or use the quadratic formula to find your 2 remaining roots. So this one happened to be a third degree polynomial, which means we only needed to find 1 before we were able to use factoring or the quadratic formula. Down the road, we're going to have a 4th degree or a 5th degree polynomial. So we'll have to do this several times until we find enough to give us a quadratic. Second problem then. Find all the roots of f of x equals that polynomial. It's a third degree polynomial, so I know that I only have to find 1 before I switch to using factoring or the quadratic formula. So on this one, I'm going to write p equals plus or minus 1. I'm looking at the factors of this negative 6 sitting right here. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. For q, I'm looking at the factors of the leading coefficient, which is 2. So I'm kind of lucky there. Plus or minus 1 and plus or minus 2 are the only factors of the leading coefficient. So now I need to write the p over q to find all of my possible rational roots. P over q is going to be, remember my trick, stick with one denominator and list all the numerators over it. Then switch denominators and list all the numerators over that one. And then keep doing that until you've gone through all the denominators. So for this one, it's plus or minus 1 over plus or minus 1, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. That takes care of the denominator of 1. Now we've got to take care of the denominator of 2. So I have plus or minus 1 divided by plus or minus 2, which is plus or minus 1/2. And then I have 2 halves, which is 1, but I already have that, so I don't got to write it down again. Then 3 halves, so plus or minus 3 halves. And finally, plus or minus 6 halves, which is 3. I already wrote that one down. So these numbers right here are all of my possible rational roots. There's 12 of them sitting there. There's only 3 roots in the entire polynomial. So obviously a lot of these aren't going to work. But if there's a rational one, it's sitting there. I just got to find 1. Set up the table. Coefficients of the polynomial go across the top. Remember to include any zeros for missing terms. We do have all of our terms here, so 2, 1, negative 7, negative 6. Now just pick one and go. Hopefully you get lucky the first time. If not, then try a different one. You want to try 1? Okay. Plug 1 in. This is synthetic division here, so the first coefficient comes down. 2 times 1 is 2. We're just not showing the addition on the synthetic division. So 2 times 1 is 2, plus 1 is 3. 3 times 1 is 3, plus negative 7 is negative 4. Is this one going to work? No. Give me another one. If it doesn't work, if you can see that it's not going to work, then I wouldn't waste your time writing it down. You want to try 2? Okay. So we'll try 2. The 2 comes down. 2 times 2 is 4, plus 1 is 5. 5 times 2 is 10, plus negative 7 is 3. 3 times 2 is 6, plus negative 6 is 0. There, I got a remainder of 0, which means that 2 is a root. And now we're left with a second degree polynomial, which is 2x squared plus 5x plus 3 equals 0. Because it's second degree, I can now try to factor it or use the quadratic formula. In my opinion, factoring is always faster than the quadratic formula. To do factoring this one, it has to be a box, so that means I need AC, which is 6. Two numbers that multiply to give me 6, but add to give me 5. 3 and 2, yeah. So my box is going to be 2x squared, and then 3 here, and then 3x and 2x, the numbers I picked. Factor out the GCF, 2x on this one, 3 here, just x on that one, 1 on that one. I'm going to make some more room here. Okay, so I have my factors now. X plus 1 times 2x plus 3 equals 0. Zero product property. X plus 1 equals 0. 2x plus 3 equals 0. So therefore x equals negative 1 is a root. And x equals, if I move the 3 over, it becomes negative, divided by 2, negative 3 halves is the other. So we have x equals negative 1, x equals negative 3 halves, and then the third was x equals positive 2. Those are the roots for the polynomial. I want to drive home one more point. Notice that negative 1, positive 2, and negative 3 halves are all sitting here. They were all there. So that's good. And up here, we could have continued on, draw a line, and then try another one. Maybe negative 1, since we got a negative 1 sitting here. If I plug negative 1 in up here, the 2 comes down. 2 times negative 1 is negative 2. 5 plus negative 2 is 3. Times negative 1 is negative 3. 3 plus negative 3 is 0. So that root also works in this route up here. Okay? But you don't have to do that once you get down to a quadratic. So I just want to point that out because we're going to be dealing with polynomials that are bigger than third degree. Okay, next one. Find all the roots of that polynomial. What should we do? P is all the factors of which number? 5. What are the factors of 5? Yep. Okay. And then Q? And that's it. So not a long list for either of those. But we still have to do what now? P over Q. Plus or minus 1. Plus or minus 5. Now switch denominators. Plus or minus 1/2. Plus or minus 5 halves. Okay, so there's only 5 possible rational roots for this polynomial. Now what? Sorry, did I say 5? 10. There's only 10, no 8. Wow, it's Monday. Now what? Start trying numbers. Yeah, set up your table. And we don't know how long this is going to take. We could get it on the first try. Maybe not, I don't know. Coefficients across the top. Do we have all our terms? Yep, so 2, negative 1, 2, 5. You picked 1? Okay, we'll try 1. 2 comes down. 2 times 1 is 2. So we get 1. 1 times 1 is 1, so we get 3. 3 times 1 is, okay, so we get 8. That one didn't work. Try 2. 2 doesn't even appear in our list. Try 5. How about negative 1? I like my numbers to stay small. So we bring the 2 down, and now we have 2 times negative 1, which is negative 2, plus negative 1, so that's negative 3. Negative 3 times negative 1 is 3. Plus 2 is 5. 5 times negative 1 is negative 5, plus 5 is 0. So negative 1 worked. Which means negative 1 is a root. Now what? Okay, so we have what? Plus 5 equals 0. So now, if we want to factor it, what do we need? Box method, and AC would be 10. Okay, so we need 2 numbers that multiply to give us 10, but add to give us negative 3. Negative 5 and positive 2, check it. Does that work? No, because I got to multiply to give us positive 10. So both signs have to be the same. Positive 5 and positive 2 doesn't add to give me negative 3. Okay, negative 5 and negative 2 still doesn't add to give me a negative 3. Do we have two numbers that work? No. So because I can't find two numbers that work and I really don't feel like struggling with this, I'm going to go to the quadratic formula. So I'll write x equals. Remember the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Yeah. So I'm going to write x equals negative 3, which is positive 3, plus or minus the square root of negative 3 squared, which is 9, minus 4 times a, which is 2, times c, which is 5, all divided by 2 times a, which is 2, so 4. All right, now I'll start simplifying. X equals 3 plus or minus square root. I got 9 minus 40. Negative 31. And that is why we couldn't find factors, because the roots are imaginary. So we wind up with x equals 3 plus or minus the square root of, well, actually I'll make it I square root 31, because 31 is prime, over 4. And that is my other two roots. It's I root 31. Can't take the square root of a negative number, so we make it I root 31. Complex number. And my other root, which was x equals negative 1, is also a solution. So all three of my solutions are sitting there, and we're done. Yeah, the plus or minus here takes care of two answers. Yep. Don't need to. No, you can leave your answer written like this. It would be 3 plus I root 31 over 4 and 3 minus I root 31 over 4, but you can leave your answer written like this. All right, see if you can do the last one on your own. P over Q. Set up your synthetic division. Find your roots. There's your P over Q, plus or minus 1, 2, 4, and 8. And then Q is plus or minus 1 and 3. There's your Q, plus or minus 1, 2, 4, 8, 1/3, 2/3, 4/3, and 8/3. So we'll skip over the trial and error and just make our table 3, 7, 6, negative 8. And apparently negative 2 works. So the 3 comes down, negative 6 plus 7 is 1. Negative 2 plus 6 is 4. 4 times negative 2 is negative 8. Plus negative 8 is negative 16. Negative 2 does not work. So, after you work your way through all of these numbers right here, you'll find out that none of them work. Yes, you're welcome. None of these work. And that's okay, because remember, it's just the possible rational roots that are sitting here. It doesn't mean that there are rational roots sitting there. In fact, this polynomial was probably generated using square roots as its roots, not actual rational numbers. So keep that in mind. It is possible for you to not be able to use this method. At this point on the homework assignment, you can do 3 problems. On those 3 problems, this will not happen. That's why I specifically picked these 3. The second theorem in this section is called the conjugate root theorem. The conjugate is when you have like a plus b times a minus b. Those are conjugates. The numbers are the same, the sign in between is opposite. The conjugate root theorem says if a plus bi is a 0, I'm writing these as complex conjugates, then a minus bi is also a 0. If a plus bi is a root, then a minus bi is also a root. This includes irrational numbers, irrational roots. If I have this form here, a plus or minus the square root of b, if I have a plus the square root of b is a root, then a minus the square root of b is also a root. That's the conjugate root theorem. So I can now give you just one root And from that, you can tell me that there must be another root based on the way that it looks. So if I tell you 3 plus 4i is a root of a polynomial, then that means that 3 minus 4i must also be a root because of the conjugate root theorem. If you think about it, on all these problems that we were solving for x and we wound up with imaginary solutions, how many did we find each time? 2. There's always a pair of imaginary solutions. So if you got one, then you know that there's another one also, because they come in pairs. The way that we use this is by coming up with polynomials that have imaginary roots. So if I tell you to write a polynomial function of least degree with roots of -1 and 5 minus I, then you can apply the conjugate root theorem. What degree must this polynomial be if I give you these two roots right here? It must be a third degree polynomial. Why? We have this one, and we have this one, and that means we must also have 5 plus I. So this is a polynomial of third degree. That's what the conjugate root theorem tells you. Now, if I'm giving you the roots, that's not the answer. If I'm giving you the roots, and I want you to write a polynomial, how do you do that? Got to think back a section or two. Multiply them all, just multiply these numbers together? No, I got to go from the roots to the factors. Let me go back to the last problem that we did that actually had answers. This problem, if x equals -1 is a root, then what factor gave me x equals -1? X plus 1. It was x minus the root. Okay? That's what we're doing here. We're going to come up with x minus each one of these roots, and then we're going to have to multiply all those together. So my polynomial, p of x, will be the first root, which is -1, as a factor. So that'll be x plus 1. X minus -1 is x plus 1. Times, and this is where it gets really fun, x minus my next root. My next root was the 5 minus I. So in parentheses, 5 minus I. Times my last root that I had to write because they didn't give it to me, x minus, in parentheses, 5 plus I. That is the polynomial. But what are we going to have to do? You're going to have to multiply it all out. That's right. I would take care of this double parentheses situation first. So let's do that. P of x equals the x plus 1 times, now x minus, we distribute the negative sign in, it becomes x minus 5 plus I times x minus 5 minus I. I'm just distributing the negative sign into those. Now it's going to be tempting for you, because you have to FOIL both of these out, to do something other than these two right here first. Why would I want to do these two right here? Because they're conjugates. It doesn't look like they are, but they are. They are conjugates. So when I FOIL these two out, I should wind up with no more imaginary numbers. And then I'll be able to multiply it times this. When I FOIL this out, I can distribute, and then go to the next term and distribute, and then go to the next term and distribute, or I can write a 3x3 box and use the box. And I highly recommend you do that so that you don't lose track of any of your terms. I need a 3x3 box. X, -5, positive I. X, -5, negative I. Okay, so the box is set up. Now we're just going to multiply. The more box problems you do, the easier this gets, but here we go. X times x is x squared. X times -5 is -5x. x times I is ix. Negative 5 times x is negative 5x. Negative 5 times negative 5 is positive 25. Negative 5 times I is negative 5I. Negative I times x is negative ix. Negative I times negative 5 is positive 5I. And then negative I times positive I is negative I squared. But I squared is negative 1. So we have negative negative 1, which is 1. So you got to kind of think a little bit on this when you do these. You cannot avoid it. You have to do it. I would do it like this. You can do distributive property if you want to, but this is definitely going to make life a lot easier. Now once we have the box completed, we combine like terms. Out here, we still have this x plus 1. So p of x equals x plus 1 times whatever I get out of this thing. Well, start with the x squared. No like terms, so we write down x squared. That one's gone. Move on to the x terms. I have a negative 5x and a negative 5x, which is negative 10x. I have, so I'll write that down, minus 10x. And those two guys are gone. I have a negative ix and a positive ix. Those disappear. I have a positive 5i and a negative 5i. Those disappear. And then I have 25 plus 1, which is 26. Now my polynomial has no more imaginary parts to it. No, we still need to FOIL this out. That's no big deal though, we just do another box problem. What form is it? We're looking for standard form. So box again. This time it's just a 3 by 2. I have x squared, negative 10x, 26, x, and 1. Multiply all that stuff in, x to the third, negative 10, x squared, 26x, x squared, negative 10x, 26. So now we can write our final answer in standard form, p of x equals, combining like terms as we go, x to the third, this one's gone, negative 10x squared plus x squared minus 9x squared. These two are gone. Negative 10x, 26x, so plus 16x. These two are gone, plus 26. There's your polynomial with these three roots. Let's go ahead and do the next one. Write a polynomial function of least degree with these roots. Basically the same exact idea of what we just did. What do we do? P of x equals, let me bring this back so we can see something. What? It's x minus the root. So x minus negative 1, which turns into x plus 1, times what? X minus, parentheses, 1 plus 2i. X minus the root, times x minus 1 minus 2i, the conjugate of the root that I was given, using the conjugate root theorem. Now what? Okay, draw a box. Do I want to draw a box right now? I would really advise you to simplify that before you try to draw your box. So p of x equals, the x plus 1 will stick around, and then inside the parentheses I'll have x what? Minus 1 minus 2i times x minus 1 plus 2i. Now the box. Box will be what? 3 by 3. What do you want to write across the top? So x negative 1 and negative 2i. And down the side, x negative 1 positive 2i. So let's read off the top row. What will it be? Negative 2ix. Good. And the middle row. Positive 1. Positive 2i. And the bottom row. 2ix. Negative 2i. No, we're multiplying, so it's negative 2 times 2, which is negative 4i squared. But I squared is negative 1, so we have negative 4 times negative 1, which is positive 4. Now, when you combine like terms, all of your i's, when you do this, should disappear. If you have i's still lingering around, then you did something wrong. Stop and go back and find your mistake right now. P of x equals, the x plus 1 is still out front, times what? Okay, the x squared is gone. Minus 2x. These two cells are gone. The 2ix and the negative 2ix are gone. The negative 2i and the positive 2i are gone. And we have plus 5. So all our imaginary parts did disappear as they should. Now what? Your next box, 3 by 2. X here, 1 here. X squared. Okay. What is my top row going to be? Good. Okay, bottom row. Good. So now I can write my polynomial, P of x equals, what is it? Five x minus 2x is 3x plus 5. So it's x to the third minus x squared plus 3x plus 5. All right, we have another example. Write a polynomial of least degree with roots square root 2 and 1 plus I. Okay, using the conjugate root theorem. Remember that a plus bi gives me a minus bi as another root. But also, a plus square root b gives me a minus square root b as another root. So how many roots do we have here? 4. How are we going to do that? A 3 by 3, a 3 by 3, and a 3 by 3. 3 of them. We can do it. The first thing we need to do is figure out what our roots are going to be. The root here is the square root of 2. You can think of that as 0 plus the square root of 2, which means that 0 minus the square root of 2 is also a root. Now I don't have to write 0 minus the square root of 2. I just need to know that the square root of 2 has a pair of negative square root 2. 1 plus I has another root of 1 minus I. So let me get rid of that, and I'll rewrite this as negative square root 2 and 1 minus I. There's my 4 roots. What degree polynomial do I need? I need a 4th degree polynomial. So I need to write all that out first. P of x equals. List out the factors being multiplied together. What do we have? X minus the square root of 2 times x plus the square root of 2 times x minus parentheses 1 minus I or 1 plus I guess if I'm listing that first one. Doesn't really matter. Times one minus I. Okay, 4 factors. We got to multiply them together. Now for this first one right here, I'm going to still recommend you do this. Simplify that first. So, actually as I do that, can I FOIL these together? These are conjugates, right? Okay, because they're conjugates, the O and the I are going to disappear. This multiplication is actually easy. So let's take care of this one now, and then as we rewrite this one, we'll simplify this. So P of x equals, FOIL those first two. X squared so it would be times, or x times square root 2, which is positive root 2x, and then negative root 2x, those go away, and I'm left with negative root 2 times positive root 2, which is negative root 4, or negative root 2 squared, which is just negative 2. So that takes care of these two. Now let's simplify these guys. So parentheses, x what? Minus 1 minus I times x plus I. Okay, so now we're down to just 3 things that need to be multiplied together. Even though we had 4 to begin with, this one's already taken care of because it was kind of easy. And now we just have a 3 by 3 box that we need to multiply. So let's take care of that. I know it's so awful. We have x, negative 1, negative I, x, negative 1, positive I. What's the top row? Good. And the middle row? I. And the bottom row? Negative I. Negative I squared, so that becomes 1. All right, combine all your like terms. We have this front term here, x squared minus 2 times, what do we get? X squared. Negative x plus negative x is negative 2x. So this one's gone, these two are gone. Ix and negative ix, those are gone. Negative I and positive I, those are gone. So I get plus 2. Now what? Yep. Actually simplified down to just needing a 2 by 3, so no big deal. And I made a 3 by 3. Yeah, felt like it. All right, the x squared, the negative 2, the x squared, the negative 2x, and the positive 2. What's my top row? X to the 4th. X, negative 2x to the 3rd, and finally 2x squared. And here, negative 2x squared, positive 4x, negative 4. Okay, so finally, P of x equals, the x to the 4th is by itself. The x to the 3rd is by itself also, so minus 2x to the 3rd. I have like terms for my x squares, but they go away. I have a positive 4x and a negative 4. That's your polynomial. 4th degree polynomial means it has 4 roots. In this case, we have 2 irrational roots and 2 imaginary roots. All right, last problem for today. What is a 3rd degree polynomial function with rational coefficients, so that P of x equals 0, has the roots negative 4 and 2i. It's the same problem. It needs to be a third degree polynomial. Notice that I have third degree polynomials all the way through, so I can't eliminate anything off that. So let's write the polynomial. P of x equals, my 3 roots are negative 4, 2i, and negative 2i. So I'm going to write x plus 4 times x minus 2i times x plus 2i. There's no 3 by 3 box on this one. But we're still going to multiply what first? Multiply the conjugates first. So this gives me x plus 4 times x squared. The old and I disappear. Negative 2i times positive 2i would be negative 4i squared, so that gives me positive 4. So it's x squared plus 4 in there. Now, stop. On a problem that's multiple choice, a lot of times you can get to a certain point and find your answer. If I FOIL this out, I'm going to have front x times x squared is x to the third, but I'm also going to have last. 4 times 4 is positive 16. And it won't have any terms to combine, so what's my answer? Don't got to finish the problem. So, with multiple choice, you can work it down to a certain point and then eliminate answers.